All right, good afternoon, everyone. Welcome to the CrySP speaker series on privacy. It's our great pleasure to have Dr. Rob Jansen, who, completely unbeknownst to him, put on an appropriate tie for the occasion, the pink tie, of course, being the symbol of the Faculty of Mathematics here at the University of Waterloo for the benefit of the internet audience. Okay, Dr. Jansen received his PhD from the University of Minnesota, like 5-ish years ago, under Professor Nick Hopper, friend of the show, who's also given talks here before. And he's going to be talking to us about shadow and Tor experimentation.
Thanks, Ian. All right, so as Ian mentioned, I'm going to talk about shadow, which is a scalable simulation tool, and how I use it for some system security research. So just really quick. Okay, hold on one second. This just worked like 3 minutes ago. Try again. Great. So just a really brief outline. I'm going to talk about shadow and how it works. What's this shadow thing? I'm going to give a research case study, a project that I worked on, a research project, where we use shadow in multiple different ways, and then talk about some future issues that are still remaining, so improvements that we can make to shadow. So before I get into this, how many of you here are working on research projects now? Raise of hand. Show of hands. How many of you have written a tool that's useful to carry out your research, whether that be a script to analyze some data or some other type of tool that could maybe be used multiple times? Yes? Okay. How many of you have made that tool available and actually pushed it out there on the internet and know of other people using it? Awesome. I commend you. So this is there's a big problem, at least in our area of research, where a lot of times tools get thrown away after you write the research paper. And one of my motivations for starting to work on shadow was to actually create something that would be useful to the broad community of researchers that work on Tor. So that's where shadow sort of started. That was like 5 years ago now, and people are still using it. I think people mail in every once in a while telling me there's problems anyway, so I think that means people are using it. So why should you care about this type of simulator? So being able to experiment with live systems, distributed systems like Tor, allows you to expedite research and development. So you can test out bugs in the software before actually deploying it onto a live network. Okay? In the case of Tor, it's especially useful for testing things that would otherwise harm users. So Tor is a privacy network. People are actually using it, and you don't want to conduct experiments on that type of network if it's going to harm the users. So you can do this in an experimentation environment where there are no real users, and then you don't have to worry about hurting them. Also, using a experimentation framework, you can understand what happens when you deploy changes to the network across all of your nodes that are running in your network at the same time. This allows you to better understand holistic effects on the network. So Shadow does these things. It was designed to run the Tor anonymity software, and so we have experimentation setups for that. But it supports simulations with other applications also. There's just a small amount of work you have to do to get a new application running inside of the Shadow framework. So before I get into Shadow, let's just talk really briefly about some options for experimentation. And then we'll get into the approach that Shadow takes. So there are some desirable properties to experimentation in general. If you'd like it to be scalable, you want to run as many nodes as you possibly can on as little hardware as possible. You'd like it to be controllable, where you can change different parameters, tweak things, set up your configurations the precise way that you want to do that. You would like it to be reproducible so that you can run the same experiment several times, and you'll get similar results so that you have some confidence that you're doing, that you understand what the simulation is producing. And accuracy is also obviously important. If you run an experiment and it's all over the place with wildly different results, then that's going to be less useful. So there's some different methods of research that exist. You could use the live network. In the case of Tor, for example, this would be hard to manage because maybe you don't control all of the nodes running in the network. It can take a while for all of them to update to the new version that you want to test out. And in the case of Tor, there could be security or privacy risks for testing a new problem across all of the nodes. You could do something like Planet Lab. Planet Lab is a distributed research network. This graph shows, so Planet Lab nodes are run by host institutions, usually universities or research centers. This graph shows a red dot every place in the world where a Planet Lab node exists. So because Planet Lab is this sort of distributed network of machines, it's similarly hard to manage. Basically, you get SSH access into all of these machines. And then it's up to you to configure them and to launch your experiment over those machines. Planet Lab is also bad at modeling. You'll notice there's a lot of machines in Europe and in the US. If you have an experiment that's communicating between those two machines, then you get the latency and the network properties that exist on the internet between those points. So you can't really say, I want my network to be this fast. You just get whatever the internet gives you. So it's less flexible in that way. Simulation generally is an approach where you implement something that's very specific. You're looking at a very specific focused problem, and it doesn't really generalize to a larger set of issues or software. And because of that, it tends to be less accurate. And emulation is normally using things like virtual machines. Because it's actually running a fuller machine, it has a larger overhead. And if you're running multiple nodes in a virtual environment, you can start to have kernel complexities with having multiple nodes running in the same kernel. So these overheads tend to be more overhead than simulation, for example. So I want to say a little bit more about simulation versus emulation, because these two approaches are very similar. So one of the benefits of simulation is that you have control over time. You have this notion of this abstract time, simulation time, and your experiment progresses through simulation time. So that's compared to real time, whereas if you're running a virtual machine, generally you have a real-time constraint. So in a virtual machine, your emulation must advance in synchrony with the wall clock. And if something in your experiment causes your machine to be bogged down by doing expensive computations, then the virtual environment could become sluggish or unresponsive. And that could cause artifacts to come up in your simulation or in your experiment. In general, it's easier to slow down something where it's running too fast than to speed up something that's become slow. So I like to think of, in the aspect of time, simulation wins because you have control over time. You can specify how things are running. And even in the case of simulation, in some cases you can run faster than real time, depending on your workload. In some cases you'll run slower than real time because you have a lot of work going on. But in both cases, you'll still end up with the correct result. And the other thing I want to mention is realism. So in terms of realistic execution, emulation tends to win because you're running the actual OS, running Linux, for example. You're running the protocols that are included in the Linux kernel. You're running applications that actually run on the OS. So in that sense, emulation tends to win in terms of realistic execution. So now I'm going to get into Shadow. Shadow is actually somewhat of a hybrid between these two approaches, although primarily it's based on the simulation approach. So Shadow is a parallel discrete event network simulator. And we'll get more into what that means in the coming slides. Shadow models routing, so it models the internet networking part, so models routing, latency, and bandwidth. It simulates time, CPU, and the OS. So for example, TCP is implemented inside of Shadow, its own variant. Sockets, queuing, threading, those types of constructs, which are normally found inside of the kernel, are implemented inside of Shadow. So Shadow is unique in, compared to most simulations in that it actually directly executes applications as plugins. And in doing that, it emulates the C API on Linux, all the function calls that are available on Linux. It has simulated counterparts to those functions. And in that way, it runs this application that normally runs in a real OS inside of the Shadow environment. By the way, please do feel free to interrupt at any point and ask questions. I'm happy if you do that. Are there any questions at this point before I move on? So the question was, why do you have to simulate sockets and TCP and et cetera? Because can't the virtual OS be used? So I guess we're trying to minimize overhead, so we're not running an entire virtual OS. The idea is to make it as minimal as possible for efficiency reasons, while still being as close to the real thing as possible. Does that make sense? So if you ran a full virtual OS, there'd be a lot more overhead involved in doing that. Actually, there's a different simulator called NS Network Simulator. Recently added the ability to run the Linux kernel inside of its network simulation environment. And basically nobody uses it because it's way too much overhead involved. And at that point, you might as well just run an emulator, a straight up emulator. So the short answer is for efficiency reasons. Yeah, can you plug in specific responses to system calls in order to dictate how it behaves? Yeah, that's exactly pretty much what Shadow does. It will, this application thinks that it's calling a regular Linux function, and Shadow replaces it with its own version of that function. So we'll get into that in a few slides, but that's one of the main techniques that allows this process to work. It's actually called function interposition, but we'll get back to that in a few slides. Others? Yeah? So the question is, are latencies between data sources addressed in the simulator, if I understand correctly? Yeah. So yes, there's a network component that will replace the internet in a live deployment. So between each host, you'll have a network. Actually, I'm just going to get into this because this is on the next slide. Do let me know if I didn't answer your question after this slide's over, though. So the simulation environment there's a few things that will be important to understanding this. Hosts, which are logical processing units. Think of these as virtual machines, if you want, although they're more lighter weight than that. Logical processing units, and each of them have independent state. Hosts can communicate with each other over this network, which contains routing elements like nodes and links, and attributes on of those routing elements like bandwidth, latency, and packet loss. So this network gives you this sort of model of these are the points that exist in my little distributed network, and this is where I'm going to attach the hosts in this little graph. And then, so you're going back to your latency question, between any 2 points on that graph, you can compute the latency between those. And so if you send data from one point to another, that data won't show up at the other side, at the other host, until that latency has been properly accounted for. The question was, what about within a host? Like memory versus cache versus SSD, are those difference in timings accounted for? Shadow does not account for that. That's sort of at, I would say, more of an extreme scale. Generally, delays in terms of milliseconds are the things that we're concerned about. So that's why network latency becomes more important than the improvements that you would see in like a cache versus a SSD. Yeah, there's definitely some things that you'd want to test where Shadow is not the right tool to use. Like this is really for network applications. Okay, so Shadow also has a global clock. I mentioned that there's this notion of simulation time, which is distinct from physical time, right? Physical time passes. Simulation time passes at its own rate, depending on how fast the workload in the simulator. And each piece of each processing task is represented by an event. An event is for a specific host and at a specific time. Okay, so we have, these are the processing units in the simulator. These events are stored in an event queue. The event queue holds events. It's a priority queue sorted by time. So there's a min heap. So you have an order of events that should occur over time inside of this queue. So given these constructs, the goal of the discrete event engine then is to facilitate communication between the hosts, the virtual hosts. Okay, so you want to allow, the simulator allows them to exchange events between each other according to the delays and packet loss rates, and et cetera, from the network. Okay, so Shadow is as fast as possible execution. So depending on the workload, it can run faster or slower than real time, but it will run as fast as it can. So the really high-level algorithm here for the engine, simulation engine, is while the experiment is still running, it gets the next event from the priority queue, which will be at the head of the queue. It sets the new time to the time that's stored in that event, so it updates the clock. And then it processes that event, which could be anything from sending a packet from one host to another, or checking a TCP socket to see if it has data incoming, things like that. Each of those events could result in additional events being created and pushed into the event queue. Okay. So then the simulation progresses by continuously executing these events until some time has passed, and then it will stop the experiment. So I mentioned that the Shadow is a parallel discrete event simulator. So this queue that I've been talking about is actually implemented as multiple queues. There's Shadow includes multiple threads. Each of these are, I call them physical threads, which are worker threads inside of Shadow. So the event workload processing these events is split up between these different threads. Each thread has its own notion of what the local time that it has, and each thread has its own event queue, and the hosts down here are separated among the threads. So in this case, there's 2 hosts for each thread. And this is one way to split up the work among different processing units inside of the actual simulator. Are there any questions at this point before I continue? All right. So because there's now threads involved, we have a synchronization problem that we need to solve. So we need to ensure that causality exists. So what this means is events need to occur in the correct order. So one thread can't have an event show up in the past where it's like this thread has a local time, it's up here in the future. If an event comes into that guy's queue, into the blue thread's queue in the past, that's an error, right? That should not happen. So in order to ensure that that doesn't happen, Shadow uses an approach called conservative synchronization. And what this does is it separates time, the passage of time here, into different categories. And it creates a barrier, time barrier between those categories. So we define a safe execution interval, which means at any point, these 2 threads, any events that are inside of this safe execution window can be executed in parallel, which means we guarantee that the green thread, for example, will never send an event to the blue thread that will occur inside of this interval. Any events that the green thread sends to the blue thread must show up in the future intervals, right? So that's a way to ensure causality. So then this is a barrier. Each thread runs its local time, its events up until the barrier, and then waits for all other threads to reach the barrier. And then the safe execution window moves to the next window. And then that continuously processes over time. The question was, what resolution do we check causality?
So it's your internal clock that you're checking causality against?
So the internal clock is the clock we're checking causality against. Yes, so there's a global clock that still exists, and then each of these guys has a local clock. So each thread itself ensures that the local clock never goes in reverse, right? So each event is in order inside of the local time. And then we know that no events, whenever an event is pushed into this thread, or into this thread's queue, we check to make sure that it's not before this barrier time, right? So any event that is transferred from the green to the blue has to come in the future. So each thread locally ensures that it's executing only in the future until the barrier, and it only sends events to other threads in the future part. So that's, by checking it that way, we ensure. I don't know did that answer your question? You don't look convinced.
You have a concept of distance.
Have a concept of distance?
Yes. Things that are far away here.
I don't understand.
Yeah, well, physics, you have a light cone. I don't know what, usually this one, but if it's far away, it's has a larger latency than something nearby.
Okay.
You're simulating things just all locally?
Each of the, maybe we should address this. Let's address this after the talk because I will talk to you about this. But
at this time, we shouldn't care about these matters.
Sorry, what was that?
The distance means that distance between two nodes, okay? It talks about the time orders, not the physical location of the nodes. Okay?
I believe you're saying distance doesn't matter.
In this topic.
I'm not sure what is meant by distance, so I don't.
Well, latency can add to the safe execution interval.
Latency is a safe execution.
Latency might add to the safe execution interval. If something couldn't get here, even though the event occurred, but it couldn't get it.
I see. So this safe execution interval, that's simulated time, which means time is, I should have mentioned this, whenever an event is executed, the simulation time is paused at that point. That event is executed at that single instant in time in the simulation time. Global time is always advancing, of course, but the simulation time is paused while that event is being executed. So these local times here are simulation times, not physical times.
I think what Lori was saying is that the green thread and blue thread, if they represent hosts that are near each other in the network topology, then an event sent from the green thread could arrive at the blue thread in a shorter simulated time.
I see.
Than if they are representing hosts that are far apart in the simulated topology.
Yes, that's absolutely.
So if you have a topology that looks like a bunch of stuff over here, a bunch of stuff over here, and a transatlantic cable in between them, you should put those on one thread and those on one thread, and then your safe execution interval is bigger.
Yes,
and you'll get more efficient.
that's absolutely correct, yes. Yeah, our safe execution interval here is the min latency between any of the nodes. But you could definitely balance that, as you just said, by putting different nodes in different locations to try to increase that min latency value. And that will expand your...
So it's not a global parameter, that's something you can tune between different...
Well, the min latency depends on the network and where your hosts are attached.
Right. At runtime, it will compute that, right? Or do you have to set it?
It will compute that at runtime, yes. But if you put all the nodes that are really, really close to each other on the same thread, then those all become local events, and you don't have to worry about. All right. So next I'll talk a little bit about the network graph. So network routing is done by reading in a representation of the network. So we use a graph model where each router in the internet is represented by a node, and the edges represent connections between the nodes. So the edges define latency and packet loss rates between those 2 points. And on each of these routers, we have IP addresses where hosts can be connected. Okay, so hosts are connected to each of these, and then the main goal of this graph is to be able to say any 2 pair of hosts, what's the latency between them? And that is used to figure out at what, how long to wait when one node sends an event or one host sends an event until it should show up at the next host. And of course, queuing and bandwidth delays also are a part of that. So we have a unique, in this graph model, there's 2 situations. If the graph is complete, meaning every host is connected to every other host with a single link, then the job is really easy, right? You look up the link, and you look up the latency between those 2 hosts, and you're done. If it's not, if you have multiple points, multiple routers in between 2 hosts, then Shadow will compute the shortest path between those 2 endpoints, sum all the latencies on the links that make up the path, and then cache the result so it doesn't have to do that for those 2 pair hosts again. Okay. So that's sort of defines the network. Next, how do we actually execute real applications on these virtual hosts? So we do this with a couple of different techniques. First, we compile the application using Clang and a custom LLVM pass. And what that basically does is it takes all of the variables that are defined inside of the program, and it shoves those all into a single object or a single structure with a very specific name. So it sort of moves around those variables to be a sub-variable of this larger structure. So what that does is it means there's a single global state variable that Shadow knows the name of because we name it during the compilation process. And when Shadow loads that library then as a plugin, it looks for that variable name and it knows it can look up the value of those variables. Okay? So all of the variables exist. We know the memory regions and the values, the default initial values of those variables, and we store that for each program. Okay? So each program is only loaded once per thread, so every thread has to do this once. Then to actually execute the application, so the application then runs as a virtual process on these virtual hosts. So remember, we loaded the state of when we loaded the plugin, we looked at all of the default state. So we saved that to an initial default state table. And then for every virtual process that should be running that program that we loaded, we create a copy of that default state in the virtual processes storage area, right? So each process then has its own state table, and these addresses are actually different addresses than the original places where those variables show up in the program. So these are just allocated on the heap separately from the actual program. Okay? So then every time one of these virtual processes wants to run, we take this state, we swap it into the program area where the state needs to be when you run a program, and we overwrite the data that's in those memory regions, and then we allow this virtual process to run, and when this virtual process is done running, then we copy the state. The state has changed as it's running. It changes its own state. When it's done running, we copy that back out into the storage area for that virtual process. So we're sort of doing this context switch where we copy process state in and out of the single program areas. So you asked if I'm actually copying memory or if I'm just swapping pointers. So it's basically a pointer. We extract all of the state during the LLVM pass into a single structure, and then we inject a pointer to that state and the size of it. So we have pointer to the state, size, and that allows us to just copy the state out once. Okay, so that takes care of virtual processes. Now, if those virtual processes themselves are running threads, we then have a new virtual thread layer that we need to take care of inside of Shadow. So this is a Shadow worker thread. This is a virtual host. The host has multiple processes running. Each process can create its own threads like a normal process would. So in order to enable this, we forked something called GNU portable threads, or pith. GNU portable threads is a library for non-preemptive cooperative threading. Unfortunately, it wasn't thread safe, so we forked it and made some modifications to make it asynchronous and thread safe, so that we could actually run a cooperative threading library inside of a threaded application. So there's multiple layers of threads going on here. So then each pith instance uses make, get, and set swap context magic to jump program stacks, and that's how we are able to run an application and not require it to return back on the program on the stack. Okay, so we have this new virtual thread layer. Each virtual process then, when it's created, it instantiates its own instance of this rpth library. And the rpth library starts with a single thread. It's the shadow thread. And what that means is, from rpth's perspective, whenever shadow is running internally, it is running inside of that rpth's shadow thread. Then we spawn a main thread inside of this rpth library, and that will be used to call the main function of the program that was loaded. And then if that program spawns its own threads using the pthread libraries, we then create, for each of those, we create a separate rpth virtual thread. Okay? So the execution flow then goes something like this. We start up here inside of Shadow. We get an event. We need to run it. The event says, send a packet to this virtual process. So we come down to the virtual process. Let's say this is running Tor, right? So we swap in all of the state for that process from that process's backup memory region, swap that into the program area, and then we swap in the rpth instance. So rpth thinks it's running in the shadow thread. We yield to the rpth scheduler. The rpth scheduler then looks at all of its threads that we created before, the main thread down here and any auxiliary threads, and it runs each of them until those threads will block. Okay? So those threads block when they make blocking system calls like sleep or wait, waiting for something, or if they read, they're blocking on a socket with having data available. Any blocking call that it makes will cause rpth to then determine that that thread is blocking, and it'll jump to a different thread using the swap context call. So once all of these rpth threads blocks, rpth then chooses the shadow thread, schedules the shadow thread, which then allows us to go back, swap out the virtual context state, virtual process state, and then go back to the scheduler and do the next event. Okay? Questions before I move on? All right. So the last component here is function interposition. So I mentioned that we're running the application, we're directly executing the application, such as Tor. Normally, distributed applications will send packets to each other, which normally go out the kernel and out of the machine's memory or the machine's network. In order to prevent that from actually going out to the network and to redirect those things back into Shadow, to keep it inside of the simulation environment, we use this trick called function interposition. So the way this works is you can define a library and set it to the environmental variable LD preload. And what this LD preload does is every time a function is called, the function symbol is first checked inside of this preload library. If that function symbol exists inside of the preload library, it calls that version of the function. If it doesn't exist, it searches for the next library that does have the symbol. Okay, so this LD preload is basically inserting your own special custom library at the top of the library list that it searches for that symbol. So this means if any of these threads try to send data using create sockets or read or write data or create threads, we can intercept all of those function calls using this LD preload trick and then figure out what we need to do to make it work correctly. So to emulate a real OS system. So for example, if a packet's being written, we then take the packet data, we send it down into Shadow, create a virtual packet for that data, and it gets shuttled into the TCP socket layer, and eventually it becomes an event and gets sent out to the other node. When the other node has that packet come in, then suddenly its socket is ready to read, so that will trigger the rpth scheduler to read that data in. Okay? So these function calls, this redirection is what allows us to be able to run real programs inside of this simulated environment. Occasionally, some function calls, for example, the write function call, write can be called on files or on sockets. So occasionally, Shadow will just revert and let the OS or other application libraries handle that. So when writing to a file, Shadow will just let libc actually handle that function call instead of having to implement that itself. But if write is called with a socket descriptor, then it has to forward that inside of Shadow. The question was, are you assuming that the process is not using memory mapping, right? I don't assume that. I believe that should still work as it normally would.
Would that be a blocking call?
Is that a blocking call? I don't think it is.
Right. It's like there seems to be a how wired in order if the scheduling is tied, if it's non-preemptive, you're swapping out on blocking calls, right?
Mm-hmm. Yeah. So there are situations where you might, for example, if you have an infinite loop, then that's going to be an issue, right? We're not going to be able to detect that. So there are cases where this wouldn't work and you would have to change your code. It's not completely generalizable.
Yeah.
But for the Tor application so far, we've been able to handle every issue that has come up by intercepting a function and doing something inside of Shadow or something like that.
I think what you're saying is you don't handle page faults as a blocking call. You just let the OS handle the page fault and you block until the page fault is resolved.
Right, yep. Okay, so I then mentioned that, so because we're intercepting all of these different function calls, what it comes down to is Shadow is sort of simulating a kernel, or at least the minimum amount of functions that it needs to implement inside of the kernel to have an application like Tor work correctly. So some of the things, I maybe mentioned sockets and queuing. This has to be implemented inside of Shadow. TCP, UDP are implemented. Threading using the techniques I discussed. Another interesting one is randomization. So if you want the simulation to be deterministic, which means you run it twice and you'll get the same exact result, then you need to make sure that your application isn't drawing entropy from the real machine, because that would change the order of events that happens during the simulation. So we actually can intercept all of the randomization functions that would normally return random data and instead return our own pseudo-random data. And CPU usage is another issue that we need to handle. So if your application, for example, is verifying, thousands or tens of thousands of signatures, and that would normally cause your application to, consume time. In Shadow, since everything is running at a single instant in time, we need to handle that. So any CPU delays that would normally happen inside of your application should get modeled inside of Shadow. So whenever you're executing inside of the program, we can track how much physical time is passing during the execution, and then go back into the event queue and push back all of the events by that amount of time. Okay. So this ends the Shadow portion of the talk. If there's questions, that would be the time.
So a bit about pushing back events. So any events that thread will do can get pushed back, but what if another event arrives during the computation portion? Like an event arrives from another thread in the future, but your thread is computing past that.
Then
Like you'll have to pick up.
I see. Yes,
Notice,
that would be an issue.
I've computed this far, and but there's an event that has I've gone past my barrier.
Right. So then your events
If you
should
ever compute past your barrier, bad things can happen, I guess.
your events should be flagged with, this is a network event that should stay here no matter what, and this is a local event that would be affected by the CPU. That's actually a good point. We don't actually do that right now, so
Okay.
should look into that. Any other questions? How much time should I leave for I guess we've been asking questions throughout, so maybe.
Sorry.
Okay. All right, so the next part of the talk was looking at some research, a research question that we explored where we actually used Shadow in different ways. I'll try to highlight the ways that Shadow was really useful here. This work is called Kernel-Informed Socket Transport. This is joint with these people here, John Geddes from University of Minnesota, Chris Watzek and Micah Scher from Georgetown University, and Paul Syverson from NRL. So I assume everyone knows Tor here. Is that true, or should I explain this? Okay, I'm getting some shrugs, so I should maybe explain just really quickly. Tor is an anonymous communication network. The reason to use Tor is to be able to access internet services without the service knowing who you are. So the way this works is a client will build a 3-hop tunnel through this Tor network. These relays inside of Tor are run by volunteers. They're contributing bandwidth to this distributed network. This client will tunnel a circuit, it's called a Tor circuit, through these relays. And it does a Diffie-Hellman key exchange so that at the end, it shares a symmetric key with each relay. Okay, so it can send encrypted data to each of these relays, and it can forward a request all the way to the exit relay, and then the exit relay will connect to whichever internet service the client is trying to access. Okay? So because Tor has been slow for many reasons, there's 3 hops involved here, so there's lots of performance implications of that. And this talk was trying to understand why Tor is slow and where congestion is happening. So we measured some relays in the live Tor network for congestion, and we did the same thing inside of a Tor network that we were running inside of Shadow. Okay, so we identified some problems, circuit scheduling and socket flushing issues from that work. And we designed KIST, which is a technique to eliminate those problems, and evaluated it in terms of performance and security using Shadow. Okay, so some background. This is a Tor relay. From the perspective of a single Tor relay, this relay may have other relays connecting to it. It may have clients connecting directly to it if it's a guard relay, and it will be connecting to other relays on the outgoing side, and it will be connecting to services if it's an exit relay. So there's lots of TCP connections coming in and going out of this Tor relay. So the Tor circuits that are created by the clients are multiplexed over a single TCP connection. So if this client is running multiple applications over here, each of the requests from those applications potentially will go over this single TCP connection between the client and the relay. Each pair of relays also has a single TCP connection. So any circuits that are going between those two pairs of relays will also be multiplexed over that single TCP connection. Okay, so let's take a closer look inside of this relay to see what's actually happening when data travels through this node. So the relay's primary goal is to forward traffic. Traffic comes in from somewhere, it forwards it to the next hop. So how does this actually work? So we have packets coming in here from the kernel on the kernel input queue. The kernel receives it from the network interface, and it separates it out into socket buffers. This is the kernel boundary. The gray area is inside of the Tor application. So Tor has a buffer that mirrors the socket buffer inside of the kernel. So when Tor reads data from a kernel, from a socket, it first reads it into its socket buffer. It then processes the data, either encrypts it or decrypts it depending on the scheme and the direction in the circuit. And then it will forward that to different circuit level queues. The circuit level queues will hold the data until it can be written out to the outgoing socket, which is associated with the next hop relay. Okay, and then in the kernel output queue, eventually those come together and are sent out on the network interface. So each of the stars here are opportunities to make a decision about traffic management. So on the kernel input boundary, Tor actually has control over which socket it reads and what order it reads those sockets in, how much it reads from them. Here in the between the Tor circuit buffers and the Tor output queue, Tor has a scheduling algorithm, so it decides which of those circuits should it read from, in what order should it read them, etc. And then similarly on the outgoing side, Tor can decide which sockets it should write first, what order it should write them in, how much it should write. And then on the network interface, there's an opportunity to make a decision before it's actually being sent out into the network. But that decision happens in the kernel. Okay, so to understand where things are getting caught up, we wanted to instrument Tor in order to measure congestion. So the way we're doing this is we have two versions of this. One where we're running it in the live network, and one that we're running inside of Shadow. So in the live network, we wrote a library called libkqtime to estimate the time that data spends inside of the kernel. So libkqtime uses libpcap, which gives it access to the packet data as it comes in on the network interface on both ends, here when it comes in and over here when it goes out of the network interface. And we use that function interposition trick that I mentioned earlier to intercept read and write calls from the sockets on the kernel to the Tor boundary here. So that gives us a point where data is traveling between the socket and Tor. So we take the data when it comes in on the network interface, and then we search for matches as that data is going inside of Tor. And then on the outgoing side, we take the data as it's being sent into the kernel, and then we match it before it goes out on the network interface. So using these timestamps, we can then compute how long it's spent in each of these locations. Inside of Tor, data, a cell is just a package. It's like a packet for Tor, inside of Tor. These packets or cells are tracked from the moment they're created until they're eventually sent out onto the kernel. Okay, so those cells, we can measure how long they're spending in each of these different buffers. So we also enhanced Shadow with multiple different algorithms that were missing at the time that we did this work. I won't get into the details here. I will mention that using Shadow, we created the largest private Tor network at the time, which I think is still the largest that's been run, at least published. 3,600 relays and 12,000 clients. This is over our internet topology graph that had 700,000 nodes and 1.3 million links. So we were trying to run a realistic Tor network, which at the time was the size of the real Tor network, approximately. So in order to measure congestion inside of Shadow, because we get a God's eye view of the network, we actually have access to every single node in this path, right? So we can track each individual data item by tagging it with a unique ID. And that unique ID we can then track all the way through both directions in the circuit. So we can track that upstream to the exit node, and from the exit node we can track it down to the client. So we get the same, we can follow that single piece of data all the way through all of these hops and all of those buffers. At each of these hops, we can track that same data and measure where it's getting caught up, where it's spending the most time. Okay, so we did both of these approaches. We measured 3 relays in the live network using the first approach, libkqtime. So the data for that experiment is here. And then we measured all 3,600 of our Tor relays running in Shadow, and the data for the congestion for those nodes are over here. So I split the data into kernel input congestion, Tor congestion, and kernel output congestion. And what we found is that with this study is that congestion normally occurs in the outbound kernel buffers, so on the outgoing side. Generally, when data comes into the network interface, as soon as that comes into the kernel, Tor is able to read that from the kernel and pull it into the application. But on the outgoing side, there's too much data in the kernel, and the network interface can't send it fast enough because of the next hop bottlenecks. And so most of the time was being spent there. So we ran this in the live network, and we were able to verify this inside of Shadow in our environment. So we found congestion normally happens at roughly an order of magnitude or worse in the outbound kernel queues versus in the other locations. Okay, so Shadow was really useful in this situation because we had this whole God's eye view over the entire network, and we didn't have to worry about harming real users, so we were able to track this information across all of the nodes. For time reasons, I'm going to skip ahead and skip the causes of congestion and skip ahead to the actual performance evaluation. So we did notice a couple of problems. We analyzed this, trying to understand why congestion was happening in the outbound kernel queue. We found some issues, and we designed a mechanism to basically don't send as much to the kernel as the kernel will accept. Try to keep each of the kernel buffers really short, really small. And then that way we can keep most of the congestion inside of the Tor process. So the main approach here was, because most of the data was spending most of the time in the outbound kernel queue, we won't write data to the kernel unless the kernel can send it, right? So we can use information that's available in the kernel through get socket opt and information, which you can use to get TCP information and compute the TCP congestion window. I guess that was on the previous slide. So the TCP space here is the congestion window minus the number of unacked packets, okay? And then multiply that by the MSS, and that will give you the amount of data that you can send into the kernel that TCP will allow you to actually send out onto the network. And if you send more than that number, TCP will throttle you because of the way TCP works, and that data will just sit inside of the buffer, okay? So our approach is to follow that space guideline and only send slightly more than what we think TCP will actually send, and then limit the amount that we're going to send into the kernel based on what the actual bandwidth capacity of the node is, of the relay is. So if the relay can only send 1,000 packets per second, only send 1,000 packets per second worth of data into the kernel. Okay? So we implemented this inside of Tor. So another nice thing about Shadow is we can implement improvements to the Tor software and then test those improvements across all nodes inside of a Shadow network without having to deploy them to all the nodes in the live network. So using this approach of limiting how much we write to the kernel, we then again ran our congestion measurement experiments, and we see that the outbound kernel congestion is reduced to less than the actual congestion that we found without our KIST improvements. Okay? So we're reducing congestion in the outbound kernel from over here by roughly an order of magnitude with our KIST improvements in place. Okay, so it reduces kernel congestion, but it increases Tor congestion. So just because it's not sending that data into the kernel, that data is still sitting somewhere, so it's still waiting around. It's just waiting in a different buffer. So this shows that in the vanilla Tor case, Tor congestion was very low in most cases. But with our KIST enhancements, Tor congestion was much higher. So all the congestion was moved from the kernel into Tor. So a logical question here would be, well, if you're just moving congestion from one place to another and not actually improving things, then why do we care? Remember, in our Shadow experiments, we were able to measure data from one end of the circuit all the way to the other end. So we could measure complete congestion over the entire path. So we did that, and we added up circuit congestion, which means how long it's taking in each of these buffers on the path. And KIST was able to reduce overall circuit congestion by about 25% across our nodes that we experimented with. At the same time as that, KIST was able to improve network latency because Tor's circuit scheduler is actually set up to prioritize low throughput traffic, like web browsing. This means that the time to the first byte is generally on a new circuit, which will be prioritized over longer-lived circuits that are downloading a lot of information. So this increases the responsiveness of those of first byte time, of network latency time. Okay. So there's a couple of security evaluations here that I'm going to skip over. But I will mention that there's two common attacks in the Tor case. One's a latency attack and one's a throughput attack. Shadow allowed us to actually test out these attacks with our enhancements in place inside of our private Shadow network, and we didn't have to worry about harming any real users, and we had control over the experiment. So it made this process much, much easier. And with that, I think I will stop. We're almost at time, and I'm happy to take any other questions that people have.
Okay, let's thank Rob.
So the question was, if we tested KIST without implementing the TCP enhancements, and would it have had a similar benefit if we hadn't implemented those TCP enhancements? I don't think we ever tested it without the enhancements.
So you didn't do it that way?
Yeah. We noticed that there was some fundamental things in TCP that were missing around the same time that we started working on this. And so this was a useful place to, I mean, ideally you want your TCP algorithm to be as accurate as possible. Anyway, so.
No? Okay, let's thank Rob again.